Okay, perhaps let us begin. Then some people usually join either via YouTube or late. Okay, so welcome everybody to this week's seminar. Our first speaker today is Garv Chauhan from Arizona State University, and he's going to talk about supernova gamma ray constraints from radiative particle decays. Maybe I'll send you a reminder when 5 minutes are left.
Thank you. Let me know. First of all, thank you, you all organizers, for giving this opportunity and inviting me to this platform to present this work. So I'll be presenting about how we can use supernova gamma ray observations to constrain new physics that undergoes radiative decays. So this is based on two different works. So one is an ongoing work with my PI here at ASU, Cecilia Lunardini, and one is based on my previous work that appeared earlier this year with the group at Virginia Tech with graduate student Andrew Gustafson and Professor Ian Shoemaker. So first I'll be discussing in regards to the sterile neutrinos. So I want to give a little brief overview about the motivations. So we know that we have discovered neutrino oscillations and they imply that neutrinos have non-zero masses. So at least two of the active neutrino states are massive. The third one can still yet be massless. So there has been a great progress to understand this 3x3 neutrino mixing paradigm, but still we need to understand how the actual neutrino mass mechanism takes place, which we don't know about. So the minimal scenario is just like for any other standard model particles that you add a right-handed partner to the left-handed species, and then through the Higgs mechanism, you can have the masses. So these right-handed neutrinos are a motivated class of BSM candidates. So you can have neutrino masses in some parameter space. They can also be dark matter, and they can also produce matter-antimatter asymmetry of the universe through this process called leptogenesis. So unlike standard model particles getting their masses, there is one extra thing. Since this Majorana neutrinos that we have added are singlet under the standard model gauge group, you can have this extra Majorana mass term for these sterile neutrinos. They are sterile because they only interact with all the other species in the standard model through their mixing with the active neutrinos. So assuming that these neutrinos are heavy, which is this condition, with respect to the vacuum expectation value of the Higgs, which is 246 GeV, and this coupling is the YD, the Yukawas for these Dirac mass matrix for the neutrinos. We see that the light neutrino mass matrix under this assumption can be written in this form. So the lightness of the active neutrino masses can be explained due to the suppression that comes from the sterile states being very heavy. So the question then becomes that if this exists, then what values of masses and mixing angles can we actually probe and test in direct experiments on Earth or through cosmology and astrophysics? So in this talk, I'll be focusing on the astrophysics part. So as an example, this is the constraints for the electron coupling for the sterile state on the y-axis, and on the x-axis you have the mass of the sterile. So as you can see, for the electron coupling type, there are a lot of different types of experiments like meson decay experiments, beam dump experiments, you have beta decay experiments here, and BBN constraints, other supernova constraints, X-rays constraints, assuming if this sterile neutrino is dark matter. So there is a variety of things here that constrain the coupling to the electron type. As we go to higher masses, it's only the electroweak precision data that kind of constrains our mixing angles. But if we go to the coupling with the tau type, we see that a lot of these parameter space is kind of very empty. So our scheme in this work would be to test if we can use the astrophysical means to constrain more of this tau coupling parameter space, especially in this regime, which the supernova is sensitive to, which is usually in the MeV to hundreds of MeV regime. as I was talking about the earlier in the electron type, that as you go to higher sterile masses, the sensitivity to the in the experiments goes low because you cannot produce these heavy states. But still, you can have some kind of constraints coming from theory because you want the vacuum of the this extended standard model to still be stable, because if you add fermions into your theory, it can make the vacuum, the metastable vacuum problem in standard model even worse. So you can have bounds from there on the mixing angles through perturbativity and metastability. So there has been a lot of work done in this regard, and more recently, with one of my collaborators, we did some work. So coming back to the astrophysical means, which is supernovae, so they represent like one of the most powerful sources of neutrinos in the universe. So an of order of 10 to the power 58 neutrinos plus antineutrinos are released, which is like almost Avogadro number squared, which is like an insane amount of particles being emitted with an average energy of around 15 MeV per particle. So it's also a lot of energy being released, and the time scale they're released in is within few tens of seconds. So just to give you a very brief overview of what a supernova is, so you have the usual hydrogen gas that collapses, forms your star, you fuse into heavier elements, release energy, and then that's how the cycle of these different stages of these stars life cycle goes on. But as you reach the stage where you form iron, what happens is the binding energy per nucleon for iron is the highest. So you cannot fuse iron further and get energy out and support this fusion process. But what supports this iron core is actually the electron degeneracy pressure, and what is formed and forms the white dwarf. But there is a critical stage when you reach the Chandrasekhar mass limit, and then this iron core cannot support its own gravity through just the electron degeneracy pressure. So what happens? It collapses. Then what happens? All of this iron is disintegrated within few seconds, and it turns into free nucleons. Also, the electrons are captured by the protons, and most of this whole of this core just turns into a proto-neutron star. So dominantly, it's just neutrons. Now the neutrons also have a degeneracy pressure, and they can support the star. So this collapse then kind of stops. But the outer layers, which are very light, and they do not yet know that the inner core has stopped collapsing, they just kind of fall on top of this protoneutron star core, and then they rebound. So then this outgoing material, the ejecta, the shock, then kind of stalls at some point, but then it is re-energized back by all of these neutrinos that are produced inside this neutron star core, and they carry a lot of energy as I discussed here, and then they deposit that energy into this outgoing shock, and then the supernova happens. So pretty complex dynamics and physics of this process, but this is heuristically what happens. So have we seen one? The answer is yes. We have seen only one from which we have observed the neutrino signal. Of course, we have seen a lot of supernovae from which we have seen the light curves, but the neutrinos from only one of those sources. So you have we saw like a order of 10-second signal, and it was in accordance to what we had calculated from theory. So how you can use this as a probe of new physics is that you can say that if there was any other new light BSM particles being produced in the core, they would carry energy in addition to the neutrinos, and then they can cool the star. They can cool the star faster, and from there you can get a bound on the parameter space of whichever new species you're interested in. In complementarity to like an energy loss bound, you can also have a energy deposition bound, which is a recent work being done on few of the particles like axions and sterile neutrinos. The basic physics is that the light curves that we see for certain stars, especially the SN2P, where the P comes from the plateau shape of the light curve that we see of these supernovae. From there, we can kind of infer how much explosion energy was actually deposited into this ejecta. And we have seen very less explosion energy stars. So from there, we can constrain that any new species that is being produced in those stars should deposit energy through their radiative decays inside the envelope less than 10 to the power 50 ergs. So that's another way to bound their parameter space. So how do you produce these new species? So for example, for sterile neutrinos, we'll consider in this case that it's dominantly produced through its coupling with the tau neutrinos. Um, and uh, and the different processes that play a role are the scattering of the neutrinos with antineutrinos or through neutrino-neutrino scattering, annihilation channels like here E plus E minuses, scattering of neutrinos of electron, positron, or the nucleons play a dominant role. If you have a coupling with mu, the last two processes also can help you in production. For the tau case, the dominant mode that plays a role actually is the scattering of the neutrons, because the although all of these fermions in the final state are kind of very degenerate, so you would think that the rate for this process is very um, suppressed, but but it is in reality it turns out it's not so much suppressed. And since you have a lot of neutrons in the core, the dominant process turns out to be scattering of neutrons. So once these are produced locally, you also want to see how they actually um, how these things are carried off outside of the star. And the conditions in the star are different at different points. So for that, what you actually use to propagate them out. It's a very simple mechanism for the case of feebly interacting particles, but it could be complex. For example, in the case of early universe. So the abundance evolution is governed by Boltzmann transport equation in the case that you do not have actual, since once the sterile neutrino is produced, it just leaves the star immediately. That's the assumption because the couplings are very feeble. So the only change in the phase space comes from the scattering. So once in the scattering they're produced, they just leave. This collisional term actually seems a little complicated here, but except the fact that if you remove this lambda term, it is nothing but just proportional to your how you calculate cross section in your vacuum diagrams for in the vacuum case. Once you insert this lambda factor, it just takes care of the fact that you have the occupation factors, the thermal occupation factors, which is Fermi-Dirac for the fermions, and is the Bose-Einstein statistics if you have bosons in the any of this process involved. Once you integrate over all the phase space and entirety of the core, you can get the differential cross section, differential luminosity for the production of the sterile neutrinos. So the production rate, if you take some reference model, for example, we took a 1D simulation from the Garking group, which was an 18.8 solar mass model with peak temperatures of 30 to 40 MeV, as you can see here. Y-axis is the temperature, and the radius is on the x-axis. And the final neutron star mass is 1.4 solar mass. And the production rate for the very light sterile, which is less than the average peak temperature of the supernova, it's actually the average energy peaks at 3 times the temperature, which is around 120 MeV. But if the mass of the sterile is very high, which is 200 MeV, far greater than a few times the temperature, then it cannot be produced with very high energies. But depending on the mixing angles, the production rate can still be very high. But they are very much produced near the mass threshold of these sterile neutrinos, like the mass threshold of their masses. So given what I discussed for the cooling and the energy loss bound, you can get very strong bound in the mixing versus the sterile mass plane. The energy loss already is very strong. You can see it can probe couplings up to 10 to the power minus 8, while for the energy deposition bound, it's very strong for the heavy masses. And you can see it can go up to even lower than few times 10 to the power minus 9. So few times 10 to the power minus 10. It becomes weaker for the lighter masses because lighter masses tend to decay and deposit their energy outside the envelope. Therefore, you do not actually get a bound. So moving on to actual part of the paper that I want to discuss, one of the previous works that appeared this year is based on the photons that are produced from the decays of sterile neutrinos outside the envelope. So we are now looking at decays outside. If these decays happens outside, if you have gamma ray observatories in or around the Earth, they can see these photons during the time a supernova happens, and from there you can kind of either discover or constrain your new physics. So the different decay modes of the sterile neutrinos are as follows, depending on what mass range you are in. So looking at first, this is the branching ratio on the y-axis and the mass here. Once you are just below the pi naught threshold, which is 135 MeV, the dominant mode for decay is the 3 neutrino mode. And the mode that goes to nu gamma, which produces the photon, it's only 1,000th the branching ratio of the total processes that it can go to, which is pretty low. But as soon as you are above the pi naught threshold, we know that pi naught can decay further to 2 gammas, and we see that the branching ratio for this shoots up to of order 1. So we would also expect that if you have heavier steriles, then it can decay to the pi naught mode and your bounds or your discovery potential would be much more higher. So how do you calculate the photon flux on Earth? So it is given by this integral for this differential flux. I can explain you the different components that you have in this particular integral. So first of all, we'll notice that this is the production rate, which I discussed earlier, also given here in the bottom. Then you multiply it with an exponential term because these steriles can decay, so they can their abundance goes down depending on at what epoch you're looking at. Fn captures that depending on what angle it is decaying at, what is the energy of the photon that reaches the detector. So it is how the decay actually takes place, and it is given in the rest frame of the sterile neutrino. So I'll discuss a bit more about this in the next slide. This B gamma is just the branching ratio to the photons. Depending on the mass of the sterile, it could be different as I showed you earlier. Last ingredient is the theta function, which just ensures that the decays that we count are only the ones that happen outside the envelope of the star and nothing else. And once you integrate over all the energy of the sterile and all the decay angles, you get your total differential flux for these photons. So this is nothing new. This was first done in 1991 by Oberauer et al. But in our work, we found that in one of the analytical cases they were looking at, they had missed a condition which changes the result a bit slightly. Coming to the distribution function for the decays of these steriles. So we are looking in the rest frame of the sterile. So for the two-body decay to nu gamma, both of these decays are just back to back. So it's just a delta function with the energy carried by each almost massless species to be half the mass of the sterile. For these two-step two-body decay, in the rest frame of the pi naught, it's a back-to-back decay. So these two gammas carry same energy in the pi naught frame. From the two-body decay of the sterile itself into pi naught nu, you can calculate how much energy pi naught should be carrying, and the um, you can boost back to the sterile neutrino frame from the pi naught frame. And what you find is that the decays for this case are independent of the angle, so they are basically isotropic. But the only condition being that the energy of these outgoing photon is bounded by a lower limit and an upper limit. So basically it's a box function. So do we have a existing limit from the existing observations? So the answer is yes. So we had this what is called solar maximum mission, which was designed to observe the sun, and it had this gamma ray spectrometer, which was operating at the time 1987 A happened. And as you can see here that it was taking data at the time. So this particular window of time is around 233 seconds. Right after that, it went into calibration, came back from the calibration from around 800 to 1500 second, but the data that is available is only for this first 233 seconds. This was analyzed by the team that was responsible for this SMM mission, and they found that the counts were in accordance with the expected background, so there was no signal. So from there, you can put bounds on your parameter space of whatever theory you're interested in. In this case, we'll set bounds on the mixing angle. But I'll also discuss what is the effect if we had data from the second time window. The data is kind of lost to history because this is something NASA has, but we don't have access to it now, or wherever they were recorded, that is not available to anyone. So this is the mixing angle versus the mass. First, we'll look at the case of 1987A, which had an envelope size of 10 to the power 12 centimeter and the actual observation time of 223 seconds. Then the bound is given by this black line over here, which is gets the most amount of the parameter space ruled out in this plot. Next, we see that one feature that I want to point out that the branching ratio does create this huge dip. As soon as you go below the pi naught threshold, you see that the bounds decrease sharply because of the fact that it can only go to a gamma through the new gamma mode, which has a branching fraction very low. Coming to the next case where you have the same envelope size but a second observation window for later times, and you see that this black dotted line actually has smaller parameter space being constrained. And the fact is that when you have a smaller envelope, most of the decays that happen in 200 seconds, they are kind of seen by the gamma ray observatory. So you do not gain anything if you have a longer observation time window. But if in the case you had a larger envelope of the star, same observation time window, you see that you actually do worse first in the first 200 seconds. But if you have a second observation time window, you actually do better, which is this dotted blue line. So the role of second observation time window crucially helps in the case when the size of the star is larger. So that's the bottom line. Similarly, what you can do is you can sum over the contribution of all these decays, the photons that you're getting from these decays over the history of the universe. So simply just sum them up by taking into account the expansion of the universe. And we require that whatever this diffuse gamma ray flux you get should be less than the diffuse flux background that has been seen by the experiments, which here we take from Fermilat, and the data could be fitted by this particular um, expansion. So our diffuse background results are follows. You see that we can, from the diffuse gamma ray flux bounds, we can constrain of the order 10 to the power minus 8 in this yellow region. You see an outlying this island in this region, and this happens exactly due to the pi naught mode. Earlier, due to the heavier masses, it's harder to produce them because the production just drops out. But once, and also the branching ratio is not high enough to gives you photons. But as soon as you pass the threshold, you suddenly get photons, but only in a very tiny window. So that's why you get this island region. Our results are not, they do not agree with the previous results from few years back, and there are a few reasons which I can talk late at some later point if anyone is interested. So for future observations, for future projections, we'll be looking at two different experiments, which is, of course, Fermilat, but also a proposed new experiment, which is eAstrogam. The coverage for Fermilat is 5 degrees, for eAstrogam is 1.25 degrees. Energy range of interest is 20 MeV to 300 GeV, while eAstrogam focuses on the lower energy ranges from 0.3 MeV to 3 GeV. Effective area is almost similar for both the experiments, which is of order 9,000 centimeters square or above. To set bounds, what we do is we restrict to only those energy of the gammas which are above 100 MeV, because that's when the sensitivity for both of this equipment is the best. So you do not want a lot of background. So that's what the is the reason to select this cut. We define also the Poisson log likelihood, because in this case of BSM physics, you usually don't expect a large number of events for in observation. So it's so that's why we are aiming for this Poisson log likelihood. As you can see, like the required number of events to set bounds in given the observation time of 223 seconds or 3600 seconds is of order 2 to 4, 2 to 5. And similarly for eAstrogam, it's 2.4 events for 3600 seconds. Comparing to the Fermilat, you can see it's almost half required for Fermilat. And the reason is that the angular coverage for eAstrogam is much better. So it's much narrower in the field of view, which gives you less background, and hence you can have less number of events to set bounds. So the bounds look as follows. So you have the mixing angles here, and you have the mass here. I've already explained some part of these curves in the previous slides. So diffuse, a constraint from diffuse background is up here around 10 to the power minus 8 with the island. Then we have the SMM bound with the black line that I showed you earlier. It now here is shown in blue. We have the energy deposition bound shown in this red. And this green band shows you the seesaw band, which is like the canonical seesaw band where it can explain neutrino masses if the Dirac-Yukawa matrix was almost diagonal, although it does not need to be. So that's why this is like just a preferred band. Then you have this work that was done previously about the in-flight annihilation, where this outgoing electrons from the decays of this new species can annihilate with the ambient electrons in the medium between the supernova and the Earth. And then you can see gamma rays from there also. So that also constrains the parameter space for the low masses of the sterils. Finally, for the future projections, we see that even with a modest time window of 223 seconds, and assuming that the supernova is at 10 kiloparsec, we can already reach mixing angles for higher masses of order 10 to the power minus 16, which is a lot. These are very small couplings. And if the supernova was even closer, like 0.2 kiloparsec, which would be kind of like a benchmark point for Betelgeuse, which is a very good candidate for a star that might go supernova soon, sometime in future. Then the mixing angles that you can probe is up to 10 to the power minus 18, which is pretty fantastic. You can see the reach for both Fermilat and eAstrogam is quite similar, although as I was discussing, the number of events that you need for each of them are a little bit different. But on the log scale, they do not make much difference. That's the kind of the bottom line here. So they both have very good sensitivity, and it basically depends more on the distance to this supernova progenitor, uh, if not anything else. So given that the same plot for the tau coupling, we see that we can go pretty much very down below in the mixing angles in the same energy range of tens to hundreds of MeVs. Now coming to their new work that we are currently in progress with the Cecilia. And it concerns not the decays outside, as I was discussing just in about the previous work that is from this year, and neither it is energy deposition or anything to do with the deeper part of the star. We are more concerned here with the decays that happen near the surface layer of uh, the stellar envelope of the supernova progenitor. And the idea comes from the idea based on standard model where there is a neutrino signal you have, and that neutrino supernova neutrino burst, when it's going through all of these material layers, interacts with the hydrogen layer at the very top stellar surface, and then it induces IBD. From IBD, you get positrons, and these positrons, when they annihilate at rest near the edge, they give rise to 511 keV line, which is a very distinct signature. And it kind of gives you a one-to-one correspondence with the neutrino burst to a gamma ray echo in 511 keV. So that's what the idea is based on. But it is a bit different because we are not directly producing positrons if, for example, if you have a radiatively decaying species. For example, for this work, we are looking at axions because it's a bit of a simpler example, and also gives you something more than compared to the standard case. So you have a radiative decay of any new BSM species, here axions, which produces these high energy gamma ray photons from the decays. In the presence of the atomic nuclei near the stellar surface, these gamma rays can actually undergo pair production. So this gives you a positron in the final state. So when you have this positron when it's going through the material, it scatters and it undergoes thermalization and basically loses most of its energy. When it comes to rest, it annihilates with the background electrons and gives you very quintessential 511 keV gamma rays. One of them is outgoing, one of is mostly ingoing. So you get, however number of 511 keV lines are produced, you get half of them as signal. So that's the main idea. So the original idea that I was discussing earlier is just two neutrinos through IBD positrons and gives you 511 keV line. Number of positrons that you produce in that case or any other case that we'll be studying gives you roughly the number of 511 keV photons that you see. But you can only see these photons if the annihilation for these positrons happen in a very thin layer around the surface, which is a Compton transparent region. Because if you are too much deeper inside the stellar surface, then these 511 keV lines, even if they're produced, they cannot, they get attenuated and they cannot exit the star. So it's a very thin layer, and if it's of the order 10 to the power 9 centimeter, and this remains the same irrespective of whatever physics you're looking at, through neutrinos or through photons or directly through positrons. The signal strength in the case of standard gamma ray echo through neutrinos is pretty tiny. So you need future detectors and a very close supernova to be observable. But in the case of new physics, this signal could actually be very stronger. And in that case, it might actually be observable even if it happens in near future with current upcoming equipments. The signal looks something like this. Why is it called a gamma ray echo? Is kind of very clear from this diagram. So you have the phi gamma over here, the light curve, and here is the time on the x-axis. Neutrino signal is shown as this dotted black line, and the gamma signal from this 511 keV line is shown as this blue curve. You can see that as the characteristic signal for the neutrinos decay on few second timeline and then undergoes an exponential decay, it is right at the same time when the gamma ray signal picks up. How it looks like to an observer is that the central part of the star brightens up, and you see that this central part is getting brighter and brighter and a little broader. And then the brightness of this ring saturates, and then it kind of expands. The characteristic time scales over which this signal happens, this light curve happens, depends directly on the envelope size. If it's 10 to the power 12 centimeter, it's afforded 200 to 300 seconds. But if it's large enough, it could be up to 1000 seconds or more. We are considering the case of heavy axions, where it can be produced in the supernova core through its coupling through photons, which is denoted by this Ga gamma gamma. So it could be produced either through Primakov process or through coalescence process, where a gamma can scatter off the charged species like electrons or any other charged species in the background and gives you an axion in the final state. Either you can have two thermal photons coalescing and giving you an axion in the final state. So for light axions, lighter in the sense like compared to 100 MeV, 1 MeV is lighter. These lighter axions are produced dominantly through the Primakov process, and through coalescence you produce the heavier ones. So the coalescence process dominates for heavier masses, and I'll talk about the reason just now in the next slide. So firstly, we have discussed how the production happens, but why Primakov dominates for lower masses. So what happens is, if you look at this energy loss rate, for example, it's directly proportional to this quantity Fp averaged. Fp average depends on this particular numerator. You can see that if the mass of the axion is lower than the temperature scale, then you basically have no dependence on the mass and it's basically controlled by the temperature. But uh, if you have the mass greater than the temperature scale, the maximum dependence is of order ma squared. While for coalescence process, it's actually proportional to ma to the power 4. So it's pretty strong function of axion mass, and that's why it takes over for heavier masses. Second step after production in the supernova core is that they escape and then they decay to photons, which is given where the mean free path for this decay length is given by this in terms of the axion photon coupling. Next step is once you have this high energy gamma rays, they pair produce in presence of nuclear field, which is dominantly the hydrogen envelope in the case that we are considering, uh, which is the usual envelope for most of the supernova, core collapse supernovae. I'll not discuss details about the production, but if you have any questions, I can take them later. Once you have the pair production happening, you have the positron, which is also quite energetic. And then what you want to calculate is how long it takes in the supernova envelope for this positron to come to rest, which can be calculated from the energy loss rate, which is this differential with respect to the distance that it traverses. Depends more crucially on this ionized electron density, because the dominant process for them to lose energy is actually scattering of the excitation of these plasma electrons. Expression is given as follows. The distance calculation can simply be done by integrating this energy loss function from some initial energy, which is pretty energetic, to its rest mass energy, and you get the overall average thermalization distance. There's also a second possibility that the positron doesn't come to rest, and before it comes to rest, it just annihilates in flight. And that is what's called the in-flight annihilation probability, which is given by this particular relation. We have checked that for the energies of interest, it's only 10 to 20% in our case. So 80% of the time, it will annihilate at rest. And since it annihilates at rest, it will give you a 511 keV line, which will not be possible in the case if it has an.
We have 5 minutes left.
How much?
5 minutes.
Okay, I'll speed up a bit. Thanks. So next you produce these, you stop these positrons, and then what you do is they annihilate. And they annihilate within this Compton transparent region, as I was telling you earlier. and it's of order 10 to the power 9 centimeters. And once this annihilation happens, it gives you your 511 keV signal. Collecting all the ingredients, what I have discussed earlier, we can get the flux on Earth, and it's given as follows. So I'll explain the ingredients that are here for this integral. So once you have the production rate for this axion, you also put in the exponential because these particles decay and you lose their number density. You also want, you're only taking into time periods which are greater after the post bounce. And this dr times gamma decay uh, calculates number of decays that happen some within some width dr. So overall, this first part gives you number of axion decays that happen and gives you number of photons that are produced. Given the number of photons, we want to calculate how many of them pair produce. So this is the attenuation probability that propagating from some production point to R to X, where the pair production takes place. The probability to actual pair produce is given by dx time gamma pair. So this combination calculates how much photons are how much pairs you actually produce. 0.9 is the probability to actual annihilate at rest. And this box function over here takes care of the fact that you only take into account 511 kV line if it's produced within that Compton transparent region. So that is the full physics of this integral. Once you integrate this over taking the angular sizes into account, you can calculate the light curve for this case. So there is an existing bound from the observation of the Pioneer Venus orbiter, which was in orbiting Venus at the time. And its data is consistent with just background only expectation, as you can see over here. And from there, you can get a bound, existing bound on the axion photon coupling. For future sensitivity in the 511 keV range, we are looking at COSI and Amigo. For COSI, you have 20 centimeter square effective area. For Amigo, you have 3000 centimeter square, so it's huge. Angular resolution of COSI is less than 4.1 degrees, and for Amigo, it's of order 3 degrees. This is the background expectation for the galactic background, and this is the assumed stellar radius. So the final plot looks like this. So this is the axion photon coupling on the y-axis, axion mass here on x-axis, and then you have some existing bounds from BBN, some existing supernova 1987A bounds, as I discussed in, it's similar how it was for sterile neutrinos, some existing bounds from the gravitational wave event that we saw for the binary neutron star merger in 2017. The results for our case from the Pioneer Venus orbiter for the 511 keV line, you can see it's not the most stringent bound, but it is a good proof of principle that it does a very good job constraining the axion photon coupling. So this is where it is of around 10 to the power minus 11. If you have future observations for a 10 kiloparsec away supernova, you can see that COSI can give you some more information in this particular region, which is unconstrained. With Amigo, you can do much, much more better. And for heavy masses above 200 MeV, you can see that it does a very, very good job. So that shows how useful the observatories in this MEV gap can be, which has been quite unexplored as of now, and how it could actually be used as also a probe of new physics.